All right, guys, once again, I'm going over limits. Just to review the definition, a limit is where y wants to approach as x approaches a certain value. So if we take a look at this graph over here, I just drew a generic f of x that basically we learned in our previous video that we're trying to approach x equals a. But what we just figured out is that it's two-part. In other words, I'm going to get my red direction. In other words, I want to approach x equals a from the left side. There we go, right there. And I'm going to approach x equals a from the right side. So I'm going to take both a left-hand limit and a right-hand limit and hope that I meet somewhere. So in this case, the limit as x approaches a is at that point over here. And I tried to draw an identical curve, but you notice that there's a hole in this particular graph enlarged for detail. Once again, I want to figure out the limit as x approaches a from the left side. There we go. And as x approaches a from the right side. Once again, a limit doesn't care whether the point actually exists or not, because in this diagram, the point exists. In the other diagram, the point does not exist, and yet the limits are identical. They still meet at the same spot. But in this diagram, x equals a is legal, whereas x equals a over here is 0 over 0. So just to piggyback on what we just learned, remember, always, always, always apply direct substitution as your first option. So just to review again for the millionth time, let's say I plug in x equals 2 to x plus 2 over x squared plus 5x plus 6. Let me get my highlighter, because now that I'm using red and green, I don't want to confuse you guys. Are you doing the left-hand limit or the right-hand limit? Well, in this, we're just going back to what we previously learned. Okay. Come on, highlighter. There we go. So in this diagram, 2 plus 2 is 4. 2 squared is 4. 5 times 2 is 10 plus 6. So that would be 4 over 4 plus 10 is 14 plus 6 is 20. So 4 over 20, or 1/5. So in other words, the limit as x approaches 2 for x plus 2 over x squared plus 5x plus 6 is 0.2, or 1/5. But if I take a look at this part, this is the part that you really like. If I plug in -2 in this diagram, and I do everything appropriately, -2 plus 2 is 0. -2 quantity squared is 4. First things first, let me get my highlighter. There we go. Right. There we go. And we've got 4 plus -10. 5 times -2, and then plus 6. 4 minus 10 is -6. -6 plus 6 is 0. So in other words, the difference is that we get a hole here. We do some factoring. The limit as x approaches -2, or L'Hopital's rule, whichever is your pleasure. But you guys are going to college, and your professor's going to be like, "Hey, who taught you this L'Hopital rule? You're not allowed to use that. That's only for VIP." I don't know. I'm just kidding. I don't know the VIP of L'Hopital. So that factors into what two numbers multiply to 6 and add to 5? 1 times 6? No, 1 plus 6 is 7. 2 plus 3. 2 times 3 is 6. 2 plus 3 is 5. So that's x plus 2, x plus 3. And I cancel that out, leaving me with the limit as x approaches -2 for 1 over x plus 3. And I see, can I plug in -2 now? Yes, I can. So I go 1 over negative 2 plus 3 with my highlighter just to show that I'm plugging it in. And now negative 2 plus 3 is 1. So I get 1 over 1, or 1. How exciting. Now, again, this is basically what your college professor wants, is just evaluate the limit, whereas I like the story. I like the story of this, and the story of limits is about continuity. In other words, did direct substitution work for the limit as x approaches 2? Yes. So if direct substitution worked for a standard limit, that means that the limit as x approaches 2 of f of x in this diagram is 1/5. In fact, f of 2 is 1/5. Therefore, 2 comma 1/5 is a continuous point. Okay. In this diagram, though, the limit does exist. The limit is 1. The limit as x approaches negative 2 for f of x is 1, but the point negative 2 comma 1 is not defined. Therefore, this point is discontinuous. So let me just define this really quick based on our knowledge. So the theme for today is, how do you know if your point is continuous or discontinuous? So a point is a continuous point if and only if all 3 requirements are met. So not 1, not 2, but all 3 requirements. And according to the textbook, in other words, how do you know if x equals a is continuous? So f of a is defined. The limit as x approaches a of f of x exists. And the limit as x approaches a of f of x is actually equal to f of a. So for some of you guys, you may be like, oh yeah, that totally makes sense. But let me just break this down for you in colloquial terms. Colloquial is, oddly enough, is a big word for simple talk. Colloquial. So f of a is defined. What does that mean? That means direct substitution works, so the point exists. So the point exists is requirement number 1. First off, you can't have a continuous point unless the point is there. If there's a hole in the graph, I mean, you're done. It's already discontinuous. It fails. The limit has to exist. Now, refresh your memory. I'm rubbing my temples right now. You can't see that because I'm holding the iPad and I don't want to. Anyway, so remember yesterday. How do you know if a limit exists? The left-hand limit and the right-hand limit need to agree. So the limit needs to exist. The limit exists. In other words, the left-hand limit and the right-hand limit need to agree. And yes, I can't help but think about my second year of teaching this at Stanbridge. A student asked me, are you sure they're called left-hand and right-hand limits? Are you just saying that because hands make it easier for us to understand? No, they seriously are called a left-hand limit and a right-hand limit. So yes, the left-hand limit needs to agree with the right-hand limit. And so if the limit exists, in other words, the left-hand limit and the right-hand limit agree with each other, and the point exists, therefore the point actually needs to match up with the limit. So the limit has to equal the point. So just to clarify, how do you know if the point is continuous or not? The point needs to exist, the limit needs to exist, and the limit actually needs to equal the point. Think of it like a car driving on a road. It has to get from one end to the other smoothly. Okay? Okay. Remember, we're approaching x equals a from both directions. Okay, so going on, so let me just give you 4 simple diagrams. So let's say I give you something like this. I just drew you a cool line. Now remember, what are the 3 requirements to determine whether x equals a is continuous or discontinuous? Well, first things first, does the point actually exist? Yep. Right there. If I approach x equals a from the left side and the right side, do they meet at a certain point? Yep, from the left side it meets right there. From the right side it meets right there. So the limit does exist. And finally, as x gets closer and closer to a from the left side and from the right side, does that intention actually meet up with the point that actually exists? Yes. Therefore, x equals a is continuous. Now, compare that to number 2. Is x equals a continuous or discontinuous? Well, let's go over the guidelines. First things first, does the point actually exist? No, the point does not actually exist. And you'd basically be done and say x equals a is discontinuous. But if you really wanted to show your work, the point exists, but the limit does. So let me get my check mark right there. The point exists, the limit exists, but the point does not. So that's not enough information. That doesn't satisfy all 3 requirements, because therefore, how can a limit equal a point that does not exist? Anyway, now let's take a look at problem number 3. Kind of a similar vibe. So first things first, is this point x equals a continuous? Well, let's look at the 3 requirements. Does the point exist? Yep, right there. So x equals a does have a point, and that's my point. Does the limit exist? So I'm going to approach x equals a from the curve, from the left and the right side, and they meet right there. They want to go there. So the limit does exist. Now for the final requirement, does the point match up with the limit? The left and right want to go here, but the point is actually here. So the point does not actually meet up with the limit. So x equals a is discontinuous. Okay, let's take a look at this diagram over here. Well, we'll get to this, not this upcoming test, but the one after, most likely. It's called a piecewise function. The point of this is, so you get the limit. Sorry, does the point exist? Yeah, right there. Notice something though. Notice. So the point does exist. Does the limit exist? Aha, this is where we get to the fun part. From the left side, as x gets closer and closer to a from the left side, y wants to go to this black dot. But as x approaches a from the right side, it wants to go to this hole. So the left-hand limit wants to meet at this black dot. The right-hand limit wants to meet at this white dot. Let's just call this y equals 3, and this is y equals -3. They don't agree. They don't agree. So the limit does not exist according to that diagram. So x equals a is discontinuous. So I just wanted to show you guys a sample of those 4 diagrams, just to show you just how special it is to get a point that actually is continuous. Okay. All right, moving on. I'm going to go to, we already got that part. So now, limits to look out for. Remember that with direct substitution, if you get 0 over 0, that means that we approach x equals a from the left and the right, and it intends to go to a hole. Once again, calculus doesn't really care, limits don't really care where the point actually is. It's all about intent. Now comes the dangerous part, which gets people a little bit more confused. So suppose you apply direct substitution and you get a non-zero over 0, like 1 over 0, or 2 over 0, or 17 over 0, -20 over 0. Well, that means that this x equals a, as shown in the table we did yesterday, it results in what's called a vertical asymptote. This red dotted line is not actually in the diagram. It's just to show you that there's this little force field that x is not allowed to touch. So remember when we did 1 over 0, we did x equals, remember 1 over x, y equals 1 over x. And remember that x could not be 0. The bottom could not be 0. So we just got really, really close. We just kind of trolled the problem a little bit. We went x equals 0.1. Okay, x equals 0.01. Haha. X equals 0.001. Ha 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 ha. And we did it from the negative side. Negative 0.1, negative 0.01, and so on and so forth. The point is, in one direction, the graph went to y equals -infinity. But on the other side of the graph, the right-hand limit wanted to go to y equals +infinity. So let's do some examples. Okay. All right. Before we get some examples, they come in 4 cases. No, just drop it. It's okay. So let's just say I give you the 4 cases, because a lot of people get confused that it's just one simple case. It's not. Let me get my pencil. There we go. So suppose I'm just going to pick this x equals a part right here. It's going to be all over, but yeah. So the basic example is this classic example. If your vertical asymptote looks like this at x equals a, that means that the left-hand limit as x approaches a, and I'm going to use a black pencil. I'm going to use black ink just to make this quick. That means that the left-hand limit wants to go to -infinity, and the right-hand limit wants to go to +infinity. So if the left-hand limit wants to go to -infinity and the right-hand limit wants to go to +infinity, what does that mean about the limit as x approaches a? That means that the limit as x approaches a of f of x does not exist. The limit does not exist, Lindsay Lohan. Because the left and the right don't agree, the limit does not exist. Now, what if I just flipped it around? What if I did this instead? So, at x equals a, if I wanted to approach x equals a from the left side, it wants to go to positive infinity. And the limit as x approaches a from the right side, the right-hand limit, wants to go to negative infinity. So if the limit as x approaches a from the left side wants to go to positive infinity, and the limit as x approaches a from the right side wants to go to negative infinity, the limit as x approaches a does not exist. The limit does not exist, Lindsay Lohan. Okay, now I know what you're thinking. So all vertical asymptotes have limits that don't exist? Now I'm going to throw you a curveball. You might get a graph that looks like this. So once again, x equals a is right here, and there's this imaginary dotted line that it's not allowed to touch. So we've got the limit as x approaches a from the left side, and the limit as x approaches a from the right side of f of x. So if we trace the limit as x approaches a from the left side, so the left-hand limit, it wants to go to positive infinity. And if we trace the limit as x approaches a from the right side, it wants to go to also positive infinity. So remember my definition for a limit existing. As we get closer and closer and closer to x equals a from the left side, what is the limit as x approaches a for this function? Yeah, they both agree. So it's going to explode and go to positive infinity. Y will go to the sky. Y will go to the sky. Now, the last case, again, you guessed it. So then, what happens here at x equals, sorry, let me get that a little bit clearer. The camera's a little bit fuzzy. So, let me draw that a little bit less pixelated. So let's say we have this dotted line. Well, let's take the left-hand limit for case number 4. The limit as x approaches a from the left side of f of x, and the limit as x approaches a from the right side of f of x. So let's do that. The limit as x approaches a from the left side wants to go to negative infinity. And the limit as x approaches a from the right side also wants to go to negative infinity. Do the left-hand limit and the right-hand limit agree? Yes. So the limit as x approaches a of f of x is negative infinity. Sorry about that. So yeah, just to give you a vibe, just to give you a view of all 4 cases, they can go, one can go to negative infinity and the other can go to positive infinity. One can go to positive infinity and one can go to negative infinity. That means that the limit does not actually exist, because the vertical asymptote does not point towards the same direction. Whereas in case number 3 and case number 4, at that dotted line, they can both go to the sky or both go to, well, not heaven. So that means that the limit goes to infinity if they're both pointing up, and negative infinity if they're both going down. So let's do some problems. So let me give you 2 of these problems just to warm up. So the limit as x approaches 7. So first things first, I'm going to get my thought bubble, because I love thought bubbles when it comes to limits. I love to think when it comes to these limits. So I'm going to plug in 3 over 7 minus 7, and that's going to be 3 over 0. And knowing what I've known, a non-zero divided by 0 is going to result in a vertical asymptote. So this is going to be a different sort of problem than what we're used to. So knowing what I know about vertical asymptotes, I want to see which of these 4 cases is it going to be. Is the limit going to exist? Or is the limit not going to exist? So the key with this, and bear with me, we need to take the left-hand limit and the right-hand limit. So first things first, I'm going to take the limit as x approaches 7 of 3 over x minus 7. Sorry about that. Let me get my, now I'm going to use my colors. So first things first, I'm going to take the left-hand limit. So I know what you're thinking. So do I plug in x equals 7? Yes, technically you do, but I'm going to use this little notation, and I'm going to whisper to you. So I've got 3 over, and you would do this in pencil. So you would put 7 from the left side, minus 7. And what do I mean by 7 from the left side? Well, what's a number that's barely, and I mean barely, under 7? So think to yourself, 6.99999. Okay? So what happens when we plug in 6.99999 and so on and so forth? Well, 6.99999 minus 7, and I know you're going to think I'm crazy, it's going to be barely negative, right? Because 6.999 minus 7 is about negative 0.001. So what I do for this notation is I say 0 from the left side. Okay? So 3 over 0 from the left side means 3 over negative 0.0001. Now, remember, as I get closer and closer and closer to 0, it's going to explode to infinity. But what's 3 divided by, quote unquote, negative 0? Negative infinity. So the limit as x approaches 7 from the left side wants to go to negative infinity. Now let me try the right-hand limit. So let's try the limit as x approaches 7 from the right side of 3 over x minus 7. So you get the idea. I'm going to approach x equals 7 from the right side. So I think to myself, what's a number that's barely, and I mean barely, bigger than 7? Think x equals 7.001. Just barely. So what I do is I plug in 7, but specifically the right-hand side of 7. I'm not kidding. This is the notation. All I'm doing is adding color. So 7 from the right side, remember, that's like 7.00001. So a number so small, but to the right of 7, it's like 7.00001. So what would 7 from the right side minus 7 be? So 7.001 minus 7 would be like 0.001. But remember, that's positive. So that would be the positive side of 0. So first things first, 3 divided by 0 would be some sort of infinity, but because it's positive 3 divided by positive 0, I know, positive 0, crazy. That is positive infinity. So if the left-hand limit results in y going to negative infinity, and the right-hand limit results in y going to positive infinity, that means that the limit as x approaches 7 of 3 over x minus 7 does not exist. Sorry, the left and the right do not agree. I know I said I was going to do 2 problems, but I'm looking at the clock and I want to end it here so that you guys can absorb this information. We're going to be doing vertical asymptote problems on Monday.